Now that we've learned the basics of probability and have been introduced to the idea of hypothesis testing, let's actually get to some hypothesis tests. We'll start with the one sample tests of continuous data. So before we get to these things, I want to talk about what we need to report when we perform hypothesis tests. There's really 5 items that we have to report in the text or in the figure when we run a hypothesis test. So first up is the conclusion or interpretation of the test. Hopefully that's a given. Second thing is our statistical test. What test did we run? We also have to report the p-value. And then we should report the test statistic and the degrees of freedom. Now I list test statistic and degrees of freedom as optional because some of our tests don't have these. For example, exact tests are calculating an exact probability, so we don't have a test statistic by which we're deriving a probability, and if we don't have a test statistic, then we don't have degrees of freedom. Also, randomization tests lack degrees of freedom. We still generate a test statistic because we compare that to the null distribution that is generated from a randomization test, but we don't have the degrees of freedom. So we've got 5 things to report, but not all 5 are going to be reported because it depends on what tests we were actually running. Before we move on, let's also discuss rounding. So when we have a test statistic, we're going to round to 2 decimal places, usually. The exception is the Shapiro-Wilk test, where we go to 3 decimal places. And we mentioned this when we introduced assessing normality. For the p-value, we have different rounding rules based on the size of the p-value. So if our p-value is greater than 0.05, then we round basically to 2 decimal places. There's no need to go out to 3 or 4 or 5. 2 decimal places is sufficient when our p-value exceeds 0.05. If our p-value is between 0.05 and 0.001, then we will round to 3 digits. So if we have, let's say, 0.046, we would actually report it as 0.046 because it's between these 2 numbers. If our p-value is less than 0.001 but greater than 0.0001, then we go to 4 digits. So we report 4 digits all the way up until we get to 0.001. Lastly, I do say if we have anything smaller than 0.0001, then we report it as our p-value being less than 0.0001. We don't have to go any smaller than this. Just say our p-value is really small. It's less than this value. So first up will be a one sample test where we compare the means. So our question is x or the mean of x different from some prescribed value or some known value? Example type questions would be we measure several canine tooths and we compare it to the reported mean in a species description. So we have our sample mean and then we're comparing it to the mean that was published as a species description. Now the tests that we have are either the z-score test or a one sample t-test. The difference between these 2 tests comes down to our standard deviation that we use. If we are given and we know the population standard deviation, so sigma, then we would use a z-score test. If we have to calculate the standard deviation or approximate our population standard deviation, therefore we're using our S, our sample statistic standard deviation, then we will use a one sample t-test. And you'll see this. We've already seen this example when we introduce confidence intervals and why we have to use a t versus a z. So a z-score and a one sample t-test ask the same types of questions. Is the mean equal to some prescribed value, or is x, a single value, equal to some prescribed value or prescribed mean? So a z-score is rather uncommon. You normally don't have a population standard deviation, but when you do, we can perform it. So here's an example. Sample of acorns, n equals 25, has an average length of 15.8. Is this average different from the average acorn size of the species? For this species, acorn size is normally distributed with a mean of 18.7 and a standard deviation of 2.9. Note, you have the population mean and the population standard deviation. When you have these two values, you can run a z-score test. Contrast that with the one sample t-test example. The average acorn size for a species of oak is 18.7. If you collected a sample of acorns with a mean of 15.8 and a standard deviation of 2.2, then is your sample average smaller than the predicted species of oak? Again, now note here, I only give the population mean. I do not give the population standard deviation. Instead, I give your sample standard deviation. So here's our difference. Now, when we do hypothesis test, we can have either a one-tail test or a two-tail test. The decision to run a one-tail versus two-tail test depends on the biological question that we're asking, and then that depends on how you would state the alternate hypothesis. So in some cases, most of our biological questions revolve around, is this sample mean equal to this other sample mean? And then our alternate would be they're not equal. But sometimes you have a suspicion that some of your measurements should be larger, or you think they're smaller than some known value. So in that case, you can say, well, are they equal? That's your biological question. But then your alternate is that your average size is smaller than the known value, or the average is larger than some known value. So what's the difference between our two-tailed and one-tailed tests? Comes down to what area is our rejection region. So both types of tests still use a 5% rejection region. We still set alpha, the type 1 error rate, at 0.05. But in a two-tailed test, we split the 0.05, or the 5%, in both of our tails. So we have 2.5% of our values of our null distribution in the lower tail, 2.5% of our values in the upper tail. Our null hypothesis would be A is equal to B. Our alternate is that A is not equal to B. If we have a one-tail test, then all 5% will be in a single tail. So in this diagram, I list it in our upper tail. We're not doing the lower tail because we've specified a direction. So we've said, okay, we think our value is going to be greater than some known value. So all 5% is in this one tail. Our null hypothesis is still A is equal to B, but now our alternate will be A is greater than B. If our alternate was A is less than B, then all of our 5% would be in the lower tail and not the upper tail. So now that we've gone over the tails, let's introduce the z-score tests. So I'm going to use the example that we gave a couple slides previously. We have a sample of acorns that has an average length of 15.8 millimeters. Is this average different from the average acorn size of the species? So for this species, acorn size is normally distributed with a mean of 18.7 and a standard deviation of 2.9. So first off, based on this question, is this a one-tailed or a two-tailed test? Hopefully you've decided it's a two-tailed test. This question, is the average different from the average acorn size of the species, is our biological question, and how we stated it basically says we're going to do a two-tailed test. So if it's not equal, then, or if the average is equal, we're going to either reject that and then conclude that they are not equal. We didn't specify a direction. All right, so in this problem, we have some given values. We have a sample size, n, that's 25. We have our sample mean, 15.8. And we have our population mean of 18.7 and population standard deviation of 2.9. Now, what do we know? We know that if we take our sample mean minus the population mean and divide by the standard deviation, that this approximates a normal distribution, 0, 1. If we actually have our sample and know the sample size, then our mean minus the population mean divided by the standard error of the mean will also approximate a normal 0, 1 distribution. So before we did x minus mu divided by standard deviation to get a 0, 1, a normal 0, 1 distribution. Now we have x bar minus the mu over standard deviation of our average, or the standard error, and it still approximates a normal 0, 1. So our standard deviation of the mean is the standard error of the mean. So what we can do is calculate our standard error by doing 2.9 divided by the square root of our sample size, 25. And when we apply this function, then we get a normal 0, 1 distribution, and we can use our tables. Now, what's our statistical hypothesis? Our hypothesis is that our sample mean is equal to population mean. Now, that doesn't do us a whole lot of good to calculate a p-value when we're working with the table that follows a normal 0, 1 distribution. But we know that if we do this transformation, then our sample mean should equal 0. So if we do this for both sides, then our sample mean should equal 0. And now we can calculate the probability of getting data as extreme or more extreme than what we actually observe if this situation is true. Our alternate is that our sample mean is not equal to the population mean, and same thing, if we apply our transformation to both sides, then we're saying that our z-score is not going to be equal to 0. So let's calculate our p-value. Now remember, our p-value definition is the probability of getting data as extreme or more extreme than the observed value because of chance. So our question is, let's calculate the p-value that we would get in x that is less than or equal to 15.8, or a value that's greater than or equal to 21.6, given that our population is 18.7, 2.9. So how did I get these values? Well, we start with the x bar, 15.8. That is less than our population mean. So we want to know how likely is it that we're going to be 15.8 or farther than our population mean of 18.7. So we've got that. Now what about 21.6? Well, if I figure out how far I am 18.7 and 15.8, then I take that difference, and that's 21.6. So I can pull out my calculator and do 18.7 minus 15.8, and I get a value of 2.9. So 21.6 is 2.9 units above our population mean. Now, why do I do both of these? Well, it comes down to our p-value. It's the probability of getting data as extreme or more extreme than what we observed. So as extreme or more extreme is 15.8, so less than or equal to that value. Or we could also be the opposite end. We could be above it. And the reason we do above it is because we're doing a two-tailed test. Now, we don't have to do both of these. We don't have to calculate these probabilities, so both of these, to get our p-value. Because remember, the normal distribution is symmetric. So this normal with a mean of 18.7, standard deviation of 2.9 is symmetric around the mean. So if we calculate one of our probabilities, then what we can do is take that probability, multiply it by 2 to calculate our p-value. This is the basis of our two-tailed test here. So I'm going to go ahead and set up this probability. 2 times probability that x is less than or equal to 15.8. I'm going to do just like what we did on our last exam. So x minus 18.7 divided by our standard error, 2.9 over the square root of 25. So we have to use the standard error of our mean. And I'm going to do that on the right hand side. So when I do that, I get 2 times the probability that z, so this transformation converted it to a z, is less than or equal to -5. Well, I go to my table. Our table doesn't even have a -5 because the probability is super small. So 2 times a value that's extremely small is going to give us a p-value that is extremely small. This is actually less than 0.0001. So this is our test. This is our results of the test. How do we write it up? Well, remember those 5 different things that we have to include. Our conclusion or interpretation, our test that we ran, the p-value, the test statistic, and the degrees of freedom. So this would be an example write-up. There is little evidence to suggest that our sample is from the known species of oak. This part is our conclusion interpretation. Z-test, that's the test that we ran. Our p-value is less than 0.0001. I didn't give a test statistic or degrees of freedom because this z-test does not have them. Now you can say, why did I come up with this? Well, it comes up to be the p-value. This is our null hypothesis, that our sample mean is equal to the population mean. Our p-value is extremely small. So the probability that we would actually get a value of 15.8 or more extreme is really, really, really small. So if this is true, then we've got a really, really small chance to get 15.8 or worse, which means we can reject the null hypothesis and conditionally accept our alternate hypothesis, which is our sample mean is not equal to our population mean. Now that's how we do it by hand, and we've already done calculating probabilities using the Z table by hand, and it's very, very similar. How do we do it in R? Well, we do it the same way, just like we've learned in R. We already know our situation here. We already know how to calculate our probability, so it's as extreme or more extreme. We're going to calculate this probability and multiply it by 2 to account for the fact that we are doing a two-tailed test. So we would use p-norm. We want p-norm of 15.8. Our mean is 18.7. Our standard deviation is 2.9 divided by the square root of 25. So remember, we don't have a single value. We have a mean that was obtained from 25 values. So we use our standard error. And then the lower dot tail equals true. That's the default. So I'm not going to list that there because we're looking for this value to the left. And this value is to the left of our mean. So I calculate the p-norm, multiply by 2, and I get a really small p-value. So again, write-up is this. There's little evidence to suggest that our sample is from the known species of oak. Z-test, p-value is less than 0.0001. So now for practice, we have these 2 questions. What I want you to do is for each question, I want you to come up with a hypothesis, so the null and the alternate hypothesis based on our question. I want you to calculate the p-value, and I want you to have a write-up that for the results of the test. So question 1 is we have a sample of 6 crickets that have a mean tarsus of 19.6. This particular species of cricket has a mean tarsus length of 17.9 and a standard deviation of 2.5. Does your sample belong to this species? So hypothesis, p-value, and write-up. Practice number 2 is this. A male western spotted skunk weighs about 535 grams with a standard deviation of 105. You collected a male spotted skunk that weighs 635. Is this individual larger than a western spotted skunk? Do the hypothesis, p-value, and write-up. Now I do have S here. This could be sigma, or our population could be an entire sample that we've collected, and then we have an unknown individual. So don't think that this S is meaning this is a sample. Here's our population. So pause the video. Please do these by hand, and then check your work using R. For practice 1, I start by listing out all of the known variables given in our problem. So we have a sample size of 6. That's what I mark as n. Sample size of 6. A sample mean of 19.6. Population mean of 17.9. And a population standard deviation of 2.5. Our question was, does our sample belong to this species? Well, if it belongs to this species, then our null hypothesis is that our sample mean is equal to our population mean. The way the question was worded in the problem, our biological question, our alternate hypothesis then is that our mean is not equal to the population mean. So using that information, I then set up the equation for the p-value. So we want to know the probability that our sample mean is greater than or equal to 19.6. Why is it greater than or equal to? It's because 19.6 is greater than our population mean of 17.9. So if we were to look at our normal curve, our population is centered at 17.9. Our x bar, our sample, is 19.6, and we want as extreme or more extreme, which is that area, but we're also going to multiply it by 2 so that we can get that area, since they're symmetric. So our p-value would be that area under the curve. So it's p-value, x bar is greater than 19.6. We'll calculate that and then multiply it by 2 because it is a two-tailed test. So I start out by calculating our z. So we'll take our mean, sample mean minus 17.9 divided by our standard error, 2.5 divided by a square root of 6. And we've got 19.6 minus 17.9 divided by 2.5 over square root of 6. This gives me 2 times our p-value of z greater than or equal to 1.7 divided by 1.021. So I've rounded, which then gives us z greater than or equal to 1.67. Now, using my table, I will use the upper tail, and this probability is 0.0475. Now that's just one tail. Since it's 2 tails, we multiply that probability by 2, and we get our p-value of 0.095. That is our p-value. And this would be the p-value that we calculate by hand. So what would we report in our results? Well, we report that we ran a z-test, number 1. We would report this p-value, and we would write our interpretation. So in this case, the probability that we would get a sample mean of 19.6 or something more extreme just by chance is more than 0.05. So because p is greater than 0.05, we fail to reject our null hypothesis. Fail to reject null hypothesis. Therefore, we would conclude that our sample mean is equal, or approximately equal, to our population mean. Our sample mean is we conditionally accept our null hypothesis. So you'll see the write-up when we review how to do it in R. So for this problem, this is our null and alternate hypothesis, and in R, we would use the p-norm function to calculate our p-value. So p-norm, 19.6, mean is 17.9, standard deviation is 2.5 divided by the square root of 6. This time I specify lower dot tail, and it's lower dot tail equals false because we're dealing with that upper tail, 19.6 and beyond. Since this value is greater than our mean, we would use lower dot tail equals f. And then this is just the one tail. We multiply that value by 2 to get our two-tailed test. So once we have our p-value, we do our write-up. So this would be a write-up that I might use. Our sample of 6 crickets appears to belong to the species. Z-test, p is equal to 0.10. Now I rounded to 2 decimal places because, again, our p-value is greater than 0.05, so we only go to 2 decimal places. So now, pause this video and work on the second example. Practice number 2 is slightly different. So our male western spotted skunks weigh 535 with a standard deviation of 105. So this is given in our problem. This is our population mean and our population standard deviation. But in this problem, we collected a single male, n equals 1, that weighs 635. And I ask, is this individual larger than a western spotted skunk? So our null hypothesis for pretty much all of our tests when we test means is that our sample average is equal to the population average. But in this case, we have a single value. So we want to know, or our null hypothesis would be that our skunk is part of this population, which means our x, our single value, is equal to the population mean. Our alternate isn't that it's not equal, but rather that our value is actually larger. So we've set up direction. So in this problem, if we were to look at our normal curve, we're centered at 535. We found one that was at 635, and we want that area above to the right of 635, and that's the only area that we want because we've specified a direction. We don't do 2 times because this isn't a 2-tail test. This is only a 1-tail test. So what we do is set up our probability to calculate the p-value. For this, we want to know the probability that we would get a value that's greater than or equal to what we actually get if our skunk follows a normal distribution with a mean of 535, standard deviation of 105. Alright, so what we do is change this to a z, and we do that by subtracting our population mean, dividing by our standard error, and I'm just going to show you that it's our standard deviation divided by our square root of the sample size. And in this case, our sample size is 1 because we only have a single individual. So 105 divided by the square root of 1. This gives us the probability that z is greater than or equal to 0.95. I use my normal table. I use the upper tail part of it, and I obtain a p-value of 0.1711. So for this problem again, we would report our test, which was the z-test. We would report our p-value, 0.17, and we would report our interpretation, or our conclusion. So our interpretation, since p is greater than 0.05, we fail to reject our null hypothesis, and therefore conclude that x our sample is not larger than 535. So kind of go back to our biological question. Let's see how we do it in R. So here's our hypothesis. Again, it's a one-tailed test because we've set up direction in our biological question. So we're testing if our sample X is equal to our population mean of mu. If not, then we're checking to see if X is greater than mu. So in R, we use p-norm. We're checking the area to the right of 635, where our normal distribution is 535, and our standard deviation of 105 divided by the square root of 1, our lower dot tail equals f, because again 635 is larger than 535. And this gives us our p-value. We don't have to multiply this by 2 because it's a one-tailed test. So our write-up here, in this case, could be that our skunk is not larger than a western spotted skunk. Z-test, p is equal to 0.17. So as a review for our z-test, why would we use it? Well, we would use it when we are comparing a single value or a sample mean to a population of known mean and known standard deviation. How would we use it? Well, we would use the normal tables to calculate the probability that we would get our x value that's greater than some value that we've measured, or that our sample mean is greater than the sample mean that we calculated, given the information provided for the population. So our small x is either the single value or the sample mean, and our population is going to follow a normal distribution with a mean and standard deviation. We have this equation, then what we would do is convert it to a z-score, and then multiply our probability that we would obtain that we obtain from the z-table by 2 if it's two-tailed, or we just report the probability if we're doing a one-tail. Now, just to note, remember that we will take our sigma and divide by the square root of our sample size no matter what. So even if we only have a single data point, so a sample size of 1, we would still divide by the square root of 1 because we're working with the standard error. When we do this test, we are going to report that we did a z-test, that we're going to report our p-value, and we would report our conclusion. And our conclusion would be if our p-value is less than 0.05, then we reject our null hypothesis, and we basically go back to whatever our question is, our biological question is. Either there is a difference, or our sample is larger than the mean, or our sample is smaller than the mean, and so forth. If our p-value is greater than 0.05, then we fail to reject our null hypothesis. There's no difference.